Alright guys, so section 2.2 is really a lot of repeat of 2.1 and parts of 2.3. So I'm just going to kind of skip it right now and just get into 2.3 because the things that we talked about here and things we've already talked about 2.1 are really going to cover 2.2 in a necessary fashion. So this is talking about getting information from a graph of a function. Okay, so we're going to be talking about domains and ranges again. We'll be talking about evaluating functions. We'll talk about comparing function values, solving equation inequalities graphically. We'll be talking about adding, subtracting, multiplying, dividing functions using graphical approaches. Talk about increasing and decreasing functions, what that means to us, and then local and global maximums and minimums of a function. Okay. One thing that I want to reiterate to you is the need for us to understand what parent functions are. This is something that you learned about in Algebra 2. This PDF is on my website, faymathematics.pbworks.com, under section 2.3. You might have to dig a little bit to find it. You can just do a quick Google search of parent functions and find something very similar. That's how I got this. But parent functions are the simplest. So all your functions are structured in families. Okay, and a family of graphs is a grouping of graphs that share similar characteristics, and those characteristics can be expressed graphically and algebraically in their equations. And because we know they're a family, then by looking at particular equations or components to equations, I know how that should operate or work inside that family of graphs. So for instance, if I have a linear function, I know for every linear function, that number out front, my slope, how that operates for all graphs of that family. Okay? The parent function is the simplest function that we can express from that family. Okay, so called parent functions, sometimes called mother functions. So if you're reading a PDF or a video and somebody says that's the same thing. But we talked about constant functions; those are just your horizontal lines. Linear functions, we know those are exponents of 1. Okay, absolute value of this is absolute value of a linear function. They look like this V. Okay, greatest integer functions, I'll talk about those later on in another section. Those actually really affect you. Okay, you're impacted by greatest integer functions a lot, especially financially. Quadratics, and the reason I'm talking about this, guys, is we should know some key values off of parent functions, because if I understand key values or order pairs off parent functions, like 0, 0 on this one, 1, 1, 2, 2, 4, 4, negative 1, 1, negative 2, 2, negative 4, 4. If I can commit those to memory, it's going to make my life inside this course a lot easier. The quadratic, we have some key function or key points off there, 0, 0. We've got the point 1, 1. We've got the point 2, 4. Okay, now parent functions, if you want to remember, because this is symmetric about the y-axis, if you just want to memorize those and know, well, their counterparts over here are the same, they're just the x value is opposite, that's fine. But we're working with a quadratic, I need you to know those 5 points. Okay, those need to be just intuitive, they need to be instinctual. A cubic, okay, so that's an x to the third, so we've got the point 0, 0. We'll have 1, 1. We'll have 2, 8 eventually. And then down here we have the negative of those, both of them. Okay, this is a reflection across the origin. We'll talk about that being an odd function at some point. We'll have negative 1, and negative 2, negative 8 at some point. Square root, we get 0, 0. We have 1, 1. We have 4, 2. Okay, if we know those, that's gonna be So make our lives pretty easy. And then the cube root, very similar to that. We have 0, 0. But now instead of a cube root, so cube root is a number I multiply by itself 3 times to get the radicand. So 1, 1 is there. But now I'm going to go out to 8, 2. 8, 2. Okay, so if the x value is 8, take the cube root of 8, you get 2. I can take the cube root or the odd root of negative, so I will have this number here, -1, -1, and I'll also have -8, -2, which is, again, that word pair reflected across the origin. So those are some key parent functions that we maybe should have already a basic knowledge of. Now, we'll spend a lot of time still in this class with cubics, cube roots. The rest of this course talks about your exponentials and logarithmics, which you talked about a little bit in Algebra 2. Chapter 4, I believe it is, talks about the reciprocal function and rational functions, how they relate to one another. And then these down here are trigonometric functions, which we investigate in our trig course. But what's important is what we talk about over here. These are all functions. These things are all functions. So when we come over here and talk about the individual characteristics or components that allow us to analyze functions, these things are going to be true for all of these. Okay, so that's just an important kind of conceptual thing to think about. All right, so we look at this function t graphed in Figure 1. It gives a temperature between noon and 6 p.m. At our weather station. Okay. So they're going to ask us some key questions. Okay, can we find t of 1? Okay, well, t of 1, remember, so this is my independent variable. Okay, it's my independent variable. Okay, and that is time. Okay, this is my dependent, and that is temperature. I'm not sure why I've got that written down there. Let's do this. Okay, so down here on the bottom, we've got our time axis, and over here we've got our temperature axis. So when they ask me t of 1, they're telling me at time of 1, what is your temperature? Okay, so it's capital T represents temperature. So it's kind of confusing when we're talking about time and temperature. A lot of times it's capital T for temperature, lowercase t for time. So that's what's going on here. All of these are capital T, lowercase t. That lowercase t is our time here. Okay, or you can see obviously the graph I'm using is using x as well, so you can think about it that way. But at time 1, what's the temperature? Well, time 1, come up here, temperature right there, 25. So T1, 25 degrees. Okay, temperature at time 3. Come over here to 3, scroll up, see where it intersects my graph, going over 30 degrees. So temperature at time 3, 30 degrees. So now that means, this here, that's noon, 1 p.m., 2 p.m., 3 p.m., 4 p.m., 5 p.m., 6 p.m. Temperature at time 5, up here, and cross over 20 degrees. Okay, so which is larger? Time at 2, so time at 2, temperature at 2, which would be, a little bit less than 35, or the temperature at 4, which is 25. Okay, that one's going to be larger, right? Okay. It says find the values of x for which t of x equals 25. So remember, this is the temperature then. So if the temperature is 25, this is the way I like to do it. I'm going to take a line through the y value of 25. Oh, not that line though. Take a line through 25. Okay, say what are the x values then that compose those intersection points right there? X value of 1 and an x value of 4. Okay, so time of 1 p.m. and a time of 4 p.m. gives me a temperature of 25. Here it says find the values of x for which the time or the temperature is greater than or equal to 25. Well, think about this. If this is where we were equal to 25, then visually, doesn't it make all of this stuff up here, which is above 25, satisfy that condition? So the values of x that make the temperature greater than or equal to 25 are 1, inclusive, because I can be equal to 25, all the way up to 4, and be inclusive as well. So I'm going to write an interval notation here. Okay? If you want to write it in, just depending on how it asks you, you can say it that way. Okay, I shouldn't use x though, because I'm talking about the time, so I use lowercase t. So let's find the net change in temperature from 1 p.m. to 3 p.m. So net change is just the change in the temperatures from those two times. So if I look at 1 p.m., which was 25 degrees, and 3 p.m., which is 30 degrees, okay? So from 1 p.m. to 3 p.m., 25 and 30 are my two values, okay? So the net change would be a positive 5 in this case, from 1 to 3, positive 5.
It's different than what I played in college. I'm having to learn on the fly, and for him to go out in this stage, first time on Monday Night Football, and the stage not be too.
All right, so we've talked about domain and range already. So the domain is going to be the x values for which your graph is defined. Okay, so if this is red thing here is my function, then my domain is going to be these x values for which the function is defined, and the range is going to be the y values for which my function is defined. Just remember when we list these, okay, your domain, you go left from right. Okay, so that value there chronologically should show up before that one. When I talk about range, you're going from the bottom up. So that value there needs to be identified in your range before that value there. So here it says use graphing calculator to draw the graph of f of x equals the root of 4 minus x squared. I've already done that for you over here. And it asks you for the domain. Find the domain in range of f. Well, the domain is just the x values for which this thing is graphed for. Okay, so if I went through here and looked at all these ordered pairs, the infinite number of them, all of their x values are going to come from -2 to +2. Okay. Now, what we could do is set this 4 minus x squared greater than or equal to 0. Okay, and we could solve that, but we haven't really dealt too much with solving quadratic inequalities. You have to do a thing called a sign chart that's going to give you these results. So the graph here is allowing us to get this range or this domain that this algebra is something that we haven't experienced yet. Okay, so that's the domain. Now the range is your y values from bottom up. Okay, so what's the first y value I come across as I work from the bottom up? First y value is actually attached to that point right there, or that point, but it's a y value of 0. So my range first has a y value of 0, and what's the last y value I come across? It's right there, y value of 2. Okay, the domain, just remember what the domain means to me. Any numbers outside the domain. So if I try, let's say 3, I would have 4 minus 9 here. That would give me a negative root 5, or not, sorry, a root of -5, which remember that's I radical 5, and that's non-real. So that's not part of my domain. Okay, so any numbers outside that domain are going to give me a result like that inside my function. So as we can compare the values of two functions f and g visually by drawing their graphs, the points at which their graphs intersect are the points where the values of the two functions are equal. That's what we've been doing that forever. Okay, if I take and ask you to solve this equation, 3x plus 5 equals 2x minus 7, what we are really doing when we solve this by hand is we're letting this be y, let's call it y1, and we graph that. y1 equals 3x plus 5. Over here, we let this one be y2 and say, okay, well, y2 equals 2x minus 7. And what we do then is say, okay, that solution of x is where these two things cross. It's where they're the same. It's where the y values are the same. Give you this demonstration here real quick in Desmos. Alright, so first one I'm going to write y equals 3x plus 5, and the second one I'm going to write y equals 2x minus 7. So if you were to solve this equation analytically by hand without a graphical approach, you're going to find an x value to be negative 12. Okay? I mean, you can quickly do that math and get that x value of negative 12. So now I know where they're equal. Okay? If I know where they're equal, I automatically know then where they're unequal. If I want to say like 3x plus 5, when is that less than or equal to 2x minus 7? Well, let's look at this. The 3x plus 5 one is the red one. Okay, this red one. The red one is less than the blue one, meaning the red one is below the blue one. So if I were to choose an x value, okay, so let's just say that I choose like this line. See if I can draw on top of this real quick. So these light gray lines represent particular x values. I'm not sure what this x value here, so let's say negative 13 here. So that line right there represents an x value of negative 13. If x was negative 13, okay, you can see that the y value here, whatever it is, I don't care what it is right now, would you agree that that y value is bigger than the y value down here on this red line? That's the smaller one. And now, because I know where they're equal, I can say now over here to that side, the blue 2x minus 7, over here to the left of where they're equal, 2x minus 7 is actually bigger than or equal to 3x plus 5. And I'm just going to say bigger than, so I already know where they're equal. Okay, so that's this stuff to the left. And over here to the right, I would say 3x plus 5. That's the one that's bigger than 2x minus 7. And when I'm doing that, I'm saying that the y values that are expressed through this quantity, when I know what x is greater than this one here when I'm choosing a value essentially to the right of that intersection point. So the knowledge of where your functions are equal to one another automatically by default tells you where they're unequal, and then it's just a matter of us to determine how are they unequal. Okay. So the solutions of the graph or the equation f of x equals g of x are the values of x at which the two graphs intersect. The point at which the graph of g is higher than the graph of f are the points where the values of g are greater than the values of f. That's exactly what is being expressed right here. Okay. So if I've got these two functions, f and g, let's make one of them red. Let's make g red. Okay. So I know automatically here that an x value of a and an x value of b is where these two things are equal. Okay. If I look in between a and b, because that y value, so if I just put an arbitrary x value in here and look at the y value, so that y value compared to that y value, so the y value off of g compared to the y value off of f at this x value, f is below g. Okay, and that's really what we're seeing here. When I make this red, I'll ask the question, okay, if I choose a point right here on G, is it bigger than a point that is off of F? Is the Y value bigger? And it is. And I think you can argue that no matter where between A and B I put that point, no matter where you put it, it's going to be bigger than the point that is on F. So between A and B, so G is greater than or equal to F on the interval A to B here. Okay. Now what I probably should do here, the way I would make most sense to write this, is that let's write that G is greater than F on, now I'll use the open interval A to B here. So that means that I don't have greater than right on A or right on B. Okay. Over here, let's continue to look at this as the red one. Okay, now I can say, let's talk about over to the left of A. So from like negative infinity up to A, from negative infinity up to A, you would actually see that G is below F, so G is less than F. And from B to positive infinity, do we see again that G is below F? So G is less than F on both those intervals. All right. So that's kind of what is being argued here in this blue box. Okay, if you know where you have solutions for the equation, then solutions of the inequality f of x is less than g of x are the values of x where the graph of g is higher or greater, or the y value is bigger than the y value for f. Okay. So a lot of times they'll ask you, okay, can you solve this equation? Well, if I solve that equation, so it's quadratic, so I need to go 2x squared minus 5x minus 3 is equal to 0. So now I'll factor that, and I'll go, it's going to be the AC method, so I'll get -6, so that goes to what, -2 and -3. Sorry, that doesn't work. It's -6 and +1. -6 and +1, so I go 2x squared minus 6x plus 1x minus 3 equals 0. This is going to factor to 2x, x minus 3 plus 1, x minus 3 equals 0. So it gives me 2x plus 1, and x minus 3 is 0. So this is going to give me that factor is going to give me x equals -1/2, and that factor gives me x equals 3. So my hope is right now you see why we spent a good portion of this first quarter working on factoring. Okay, it becomes very important in next level concepts. So if this is where they're equal, then we must know where they're unequal. Okay. Really, all I'm going to do to determine where is this true. So I've got my number line right now. If I know they're equal at x equals -1/2 and x equals 3, if I put my number line on here and put -1/2 and put 3 on here, let's come over here to a value to the left of -1/2. Let's try -1. Okay. If I plug -1 in here, do I get a true statement? Okay, so let's put -1 in here. So -1 squared is 2, or is 1 times 2 is 2, plus 3 is 5. is 5 less than or equal to plugging -1 in over here. Okay, so plug -1 in over here, I get -5 plus 6, which is 1. That's false. That is false. Okay, so these values over here do not make this true, so they must make this one true. Okay, so from -infinity to -1, I know, or sorry, -1/2, I know that these here, all of these are going to give a similar result that this one does. Okay, now I'll try a number like 0. If I plug 0 in here, I get 3 here and 6 there. Okay, 3 on this left-hand side, 6 on this side. Does that give me a true statement? Is 3 less than or equal to 6? Yes, it absolutely is. So I know that in this question, any other value that is in this interval here, like 0, so -1/4, -1/8, 1, 2, 2.5, 2.9, all of those numbers in there are going to give me a similar relationship. So from -1/2 to 3, I'm going to have this to be true. And I'm going to put equality here. I'm going to put brackets because we had equality here. Now I'm going to try a number like 4. I'll put 4 in here. Okay, I get 16 times 2, 32, plus 3 is 39. Is 39 less than 26? No, it's not. So that must mean that these values over here are true for down here. So I'm going to say numbers that are bigger than 3 and go to infinity, and I'll union that. And let's just see real quick with a graph if that is validated. So if I say, y equals, or I'll just say f of x equals 2x squared plus 3, and I'll say g of x is equal to 5x plus 6. Okay, so I'm going to zoom out. Sorry, this was x squared. And we get that. Okay, so now we've got, so that's my function g of x. This is my function f of x. So the question was, well, where are they equal? Well, right there we see 1, -1/2, and right there we see 3. And now what we're going to do is say, okay, well, to the left of -1/2. So let's, I think I can maybe make this a little bit easier to see. Can I do it? Let me just try something real quick. X is greater than -0.5. There we go. Okay. So I'm just going to make that black so you can't see that. Okay. So I'm going to look at just the values to the left of -1/2, because right there is where they're equal. So to the left of that, they must be unequal. You see that the green one here is above the purple one. The green one is above the purple one. So 2x squared is greater than 5x plus 6. 2x squared plus 3 is greater than 5x plus 6. And that's to the left of -1/2. Well, that is this interval right here. Okay. Now I'm going to say, okay, well, what if x was, let me go, x is greater than -1/2. So let's say x is less than 3. There's my other endpoint here. So x is 3. So shade all this stuff to the left. So ignore the stuff that's shaded, and look just to the right-hand side. Okay, would you agree that the green is above the purple? Okay, if I'm on, I know it's kind of hard to see, but this gray line right here, okay, that represents an x value of 4. If an x value of 4 on the purple is going to give me a height of 26, but an x value on the green is going to give me a height of what looks like be like 35 here. Is it 35? Yeah. Okay. So for a particular x value of 4, the green one is greater than the purple one. Well, the green one was 2x squared plus 3. Purple one was 5x plus 6. So from 3 to the right, we have this to be true. So that must mean that everywhere else, okay, if, let's say I take and just block out things to the left of negative 0.5, and let's block out things to the right of 3. Okay, if I just block out the colored stuff, okay, let's, that's kind of a pain in the butt to change, I think. Not too bad. Alright, so ignore the gray stuff and just look at the stuff that's in here that is white. Would you agree that any x value that I choose, the purple is on top of the green? So the purple, which would have been the 5x plus 6, is greater than the 2x squared plus 3. But those inequalities are determined first by where things are equal. Then everywhere else they're unequal. Something that we like to talk about is when is a function, when its y values getting larger and when is its y values getting smaller as x is moving along the x-axis. Okay, so it says it's very useful to know where the graph of a function rises and where it falls. So the graph shown in this figure rises, falls, rises again as we move from left to right. Okay, so what we're saying here is from this lowercase value of a to this lowercase value of b. So those are just x values. There's arbitrary x values. Okay, what we're saying is that this y value here, let's just say that's the y value that pairs with a, and this is the y value that pairs with lowercase b. Okay, as I go between an interval, okay, if this y value here, the y value to the right, is greater than a y value to its left, then that means our function is increasing. Okay, so because and I like to, it's very obvious, I think, if you're standing here and you had to walk this curve, is your altitude changing and is it going up? So at that point you're increasing. Right here at this point, you're at the apex. You're at the what we call a maximum. Okay, so at a maximum you're neither increasing nor decreasing. Okay, but now if I continue to go at this point, so I look at y sub b, and now going this way, so if I look at like a y sub c now, from b to c, now our y values are getting smaller. So in this interval, we're decreasing. Okay, think about walking. You'd be walking, maybe losing altitude. Okay, I get here. Okay, and I'm kind of in the valley of this curve. Okay, a valley is referred to as a minimum. Okay, and at a minimum, you're neither increasing nor decreasing, but it's the transition between those two. And then as we go from C to D, then we are increasing. Okay. One thing that we need to know, and that I like to foreshadow, I like to think about things that we're going to do in calculus. These right now, these things are hard to find algebraically, maximums and minimums. Calculus has a tool that allows us to do that almost instantaneously. Okay. But we have to know that maximums in calculus, maximums and minimums, we call them extremums. Okay, those values occur when we recognize a change from increasing to decreasing or decreasing to increasing. It's called the first derivative test when you get to calculus. Okay, we like to talk about what is the interval that we're increasing on. Okay, so here we see that we're increasing from A to B. That's when we were going up, so that's why this says A to B. Now it's an open interval because at A, I'm really not doing anything. I'm static. At B, like I said, that's a maximum. You're not doing either thing. Okay, so that's why it's always an open interval. When we're talking about the interval for increasing and decreasing, it will always be an open interval. You'll never have brackets. They're going to be parentheses. Okay, F is decreasing from B to C, and that's what we're seeing here. So the definition of increase. So we can't just say, well, our definition is, did my y values get bigger or did my y values get smaller? Because the idea is, I can do this. I can look at like a point from here to a point from there. Okay, so I can look at those 2 points, and I could say, oh, well, that y value was maybe 3. This y value is 5. Oh, well, from 3 to 5, I increased. But what do you notice that happened in a particular section of that is that you actually decreased that one portion of that interval. Okay, so you can't just say, well, from one x value or one y value to another y value, because they're bigger, I know I increase. So we need a definition that eliminates that issue. So this is how we write it. It says f is increasing on an interval I. Okay, on an interval I. So right now our interval I is that right there. It's the difference between x1 and x2. Or same thing over here. It says if f of x sub 1, remember what f of x sub 1 means. F of x sub 1, that is a y value at x1. Okay, this is a y value at x sub 2. Okay, so the argument is you are increasing if the y value at x sub 1, so this y value right there, is below that y value right there when the x sub 1 was smaller than x sub 2, meaning this x sub 1 was to the left of x sub 2. So there's your, this would be your f of x1, and this would be f of x2. Okay, if this number here, for whenever that number is smaller than that number, and you recognize that because of those values, then when you evaluate and find the y value attached to x sub 1, if that x value or that y value is smaller than the y value that's attached to x sub 2, then you are undoubtedly increasing. Okay, it flips a little bit when we're going to talk about decreasing. All it says when we're decreasing, it says now the y value, that's the y value that goes with x sub 1, if that is bigger than the y value that goes with x sub 2, for whenever x sub 1 is less than x sub 2, so it's still saying x sub 1's to the left, if that y value is bigger than that y value, then you're decreasing. Okay? That is the algebraic way, the mathematical way of identifying increasing, decreasing, and never accidentally incorporating an increase when it should actually be decreasing, or decreasing when it should have been classified as increasing. I think increasing, decreasing are, visually, I think you can understand it. You can see, well, I'm going up in my y values, or I'm going down in my y values. But the way we describe it or define it is very, I think, cryptic. And that's the way mathematics sometimes is. The simpler concepts take a very difficult approach in defining them, because we want to make sure that in our definitions, nothing accidentally gets classified incorrectly. And that's essential here. One thing we need to talk about is when we talk about a interval for increasing or decreasing, we're always talking about what x values is the function increasing or decreasing for. Okay, so the increase or decrease, we use the y values to determine are we increasing or decreasing, but then we write our answer in regards to the x values that happens for. So when I look at this example here, so I've just sketched a quartic function here. Let me check the time here on there. All right, so we'll finish this one up and be done. I've graphed this quartic, And it simply says find the domain in the range of f. Okay, well, this is polynomial. This is polynomial. Okay, it is of that function f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1. Remember this thing. So then we have a sub 1 x to the first plus a sub 0. So this is one of those. I told you all of those are always going to have a domain that is all real numbers. Okay, so the domain here, negative infinity to positive infinity. Okay, the range, different. The range is different. Okay, basically what we do for the range is figure out, okay, of all the x values that I plugged in here and evaluate, what is the largest y value that I get back? That largest y value that you get back is 32. Okay, so if I want to find the range, remember what we do with the range is we put a horizontal bar down here at the bottom, and we start to drag that thing vertically. Well, this is polynomial, so the domain is all real numbers, so there should be arrows on here, which basically tell me then the range is any negative number that I see down. My biggest negative number will be negative infinity that I encounter. As I move up, my largest y value that I encounter will be 32. So my range is negative infinity up to 32, and I can incorporate 32. So that's my range. Now it asks us to find the interval on which this thing is increasing and decreasing. Okay, so here's the question. What are we doing as we move across this, okay, for these x values? At this juncture here, I have a y value of like negative 11. As I move to the left, those y values go up to like negative 5, they go up to 0, they go up to 1/2, and eventually they get here to a y value of 5. As I'm moving from this x value, this set of x values to the right, we can see that my y values are increasing. Okay, so on this interval here, let's highlight it here. So right there on that, those are the x values for what my y values are increasing. So that's what I'm answering the question in regards to. So the increase, so I'm just going to go from negative infinity up to negative 1. Those are the x values for which my graph is increasing. Okay, so I like to put my intervals like next to my graph, and then I'm just going to say, okay, well, that's where they were increasing. So I put an arrow up, and then I'll answer a little bit more formal over here in a moment. Now let's look at the next interval. So now I'm here, and I'm going down. These y values are going down. So going down. So what's the x values that they're going down for? It's these x values right there. So I'm going to make that green interval. That goes from negative 1 as an x value to 0. Now remember, I'm not going to include that point right there because that point is not, that's a maximum. That there's no increase or decrease from there. Okay, but in that green one, we were going down. Now, if we look at this, we'd be climbing again, and we get to point D, and that would be our maximum. So we're climbing, so that's increasing. And what are the x values that we're increasing for? So the y values tell us we're increasing, and we answer that we're increasing on the interval from 0 to 2. So when they say, on what interval are you increasing, that is asking you on what values of x are your y's getting successively bigger. Okay? And then the next question is, what happens after point D? Well, you start to go down. Your y values are successfully declining or decreasing. So what x values is that happening for? And it's all of those from 2 to infinity, so we're decreasing. So they're going to ask you, when is this increasing? So this is the increase. I'm going to say that this is the decrease. So they were increasing from negative infinity up to negative 1. And I'm going to union that with then the other place that it was increasing, 0 to 2. Decreasing from -1 to 0, and I'm going to union that with the other part that is decreasing 2 to infinity. It says finding the largest and smallest values of functions is important in many applications. In that place where we change from increasing to decreasing or decreasing to increasing, we see a change in behavior, identifies that largest or smallest value. Okay, that identifies our maximum minimum, and that's where we'll pick up tomorrow with maximum minimums. Your assignment right now that is posted, you can maybe answer a few of those questions on there. It's a lengthy assignment, so I'm putting it open until Friday evening right now. But approach that right now, go through. You might have to go through all 25 questions on there to see which ones you can answer, just so tomorrow you don't have 25 of them to do. And we can dwindle that assignment progressively through the next couple of days.